These are notes for AP Calculus, AB. This is 5.5, and we're going to be talking about differential equations and some applications of differential equations. So the beginning here is going to be a little bit like review or just some tougher differential equations than we've seen so far. And then we'll get into the application of some differential equations here. So example 1, I've written down here, dy dx is 3x times x cubed minus 4 squared. So the first thing we're going to want to do, like always, is separate our variables and move dx over to the right side. And then we're going to go ahead and start to integrate. Now, in order to integrate on the right side, we might need to use substitution. So we're going to check out here if u substitution will work by letting u equal x cubed minus 4. All right, so just over here on the side, we're going to see if this will work. So if u is x cubed minus 4, then the derivative of that is 3x squared. And of course, we multiply dx over. And we're looking for this to match our leftovers. Now, while we have a 3x and a dx, I don't have a 3x squared. So you might think, well, divide over anything that doesn't match. Except we're not allowed to do that when it comes to variables. You're only allowed to do that with things like the 3 and other numbers. So if I can't divide an x over, because I'm not allowed to mismatch variables here, then this doesn't match. And there's really no way to make it match. So the substitution is just not working. And lucky for us, the power of 2 is not so big that we can't work with it. So we're just going to work this one out the long way. I'm going to keep my integral dy with me here. And then on the right side, start multiplying this out. So instead of the u substitution, we're going to go ahead and square x cubed minus 4. So we get x to the 6th minus 8x cubed plus 16. And then I want to distribute 3x into all these terms. So we end up with 3x to the 7th power minus 24x to the 4th plus 48x. So integrating on the left, we get our y plus c, and we've been talking about dropping the c on the left. So because in the end, we're going to subtract this constant from the other constant to end up with the one constant on the right side, we are just going to stop writing plus c on the left side, and we'll only worry about writing plus c on the right side. So we'll keep on with our integration, 3x to the power 8 over 8 minus 24x to the 5th over 5 plus, this will give me 48x squared divided by 2 is a coefficient of 24, and then plus c. We don't have any initial conditions here to work with, so this is going to be our answer for number 1. All right, moving on to problem number 2, we have 2 variables. So we have to multiply dx over to the right. We also need to divide y squared over to the left. So 1 over y squared dy leaves me with 5x squared plus 3x to the negative 2 times dx. And it's just about ready to integrate, at least on the right side it's ready. So I'm thinking on the left side to rewrite 1 over y squared. Just like the 3 over x squared is 3x to the negative 2, we're going to rewrite 1 over y squared as y to the power negative 2. I'll just do it right here. So now we want to integrate on the left side. So we're going to add 1. So y to the power negative 1 divided by negative 1. And again, we're going to leave the plus c just for the right side. So here we have 5x cubed over 3 plus 3x to the power negative 1 divided by negative 1. And then here we have our plus c. So we have quite a bit to do here just to clean this up because I want to solve for y. So right now, this is going to simplify to -1 over y. So it will be negative, and y needs to be in the denominator to have a positive exponent. The other terms, these are okay. 5x cubed over 3. Then we have -3 over x. So 3 divided by -1 is -3. And we move x to the denominator. So now I'd like to divide this negative over. Okay, in dividing the negative to the other side, so maybe I'll write this down. Divide by the -1. We end up with 1 over y equals -5x cubed divided by 3 plus 3 over x plus c. And this is what gets most people. C is a constant. It doesn't work like x being a variable where you multiply or divide by a negative. It changes its sign. Because it's a constant and we have no idea if that constant is positive or negative right now or even 0, we don't know how that negative will affect the number. So it just becomes a constant divided by a number is just another constant. It will always be plus c until you know what c is. All right. So the next thing we need to do is solve for y. Now y is in the denominator. So easiest thing to do would be to flip this fraction and write it as y over 1. Well, if I flip the left side, then I have to flip the right side. What's actually happening is you're basically raising both sides to the power of -1. Now when you do that to the right side, you don't do that to each term individually. Just like squaring both sides of an equation, you're raising the whole thing to the power -1. And what happens is all of it flips over as one big group, and it becomes 1 over -5x cubed over 3 plus 3 over x plus c. So the whole thing ends up in the denominator with a 1 on top. And you would think, okay, well, that's what y is equal to. So I should be done, except we're not supposed to leave any answers as complex fractions. So we have these little fractions here in the denominator that we want to get rid of. So we need to multiply everything by the least common denominator, which is 3x. And we're almost done. So this is y equals 3x in the numerator. Here in the denominator, when I distribute 3x, the 3's reduce and I'm left with -5x to the power 4. Distribute to the second term, the x is reduced and we're left with 3 times 3, which is 9. And when I multiply 3x with the constant, so 3 times the constant is just like doing the constant divided by a -1, and I just get another constant. So when you multiply or divide by any number to a constant, you just end up with that constant. But a variable times the constant. So imagine if this was some number that we knew. 3 times that number, it absorbs the 3 and becomes a new number. But what about x times that number? It becomes the coefficient of x. So 3 times c is still c. X times c is cx. And that is our answer for number 2. Okay, so this was the review for the differential equations. And the next thing we're going to do is look at some applications. So I'm going to kind of take you back to Unit 3, where we talked about position, velocity, and acceleration. So you can see the chart I have here, and if you need to pause the video to write it all down, you should do that when you're ready. So you're going to see in Unit 3, we talked about position, velocity, acceleration. You can refer back there to kind of read more on it. So I've given you all the basic stuff we need, like position, s of t, velocity, v of t, acceleration, a of t. Velocity is the derivative of position, acceleration the derivative of velocity, or the second derivative of position. And then our units, our position would just be in feet or meters or something else. Velocity is feet per second, meters per second, it's a rate of change. Acceleration is that rate of change over time. So feet per second, meters per second, okay? What we're doing now is working backwards. We're going to start with acceleration and work our way back to position. And the way we do that is by integrating and integrating again. So this is starting with an equation of acceleration, and that's what makes it an application of differential equations. All right, although maybe a bit of a simpler one. So you're going to have two examples here that we'll go through. And all you do is you begin with a constant of acceleration. You're usually given some information about maybe the initial velocity or initial position so that you can generate the position function. Okay, so this is very similar to the differential equations where we've been given an initial condition, a point to plug in to solve for C. So they're going to be giving us values in these problems to solve for those constants as we go. So in our first problem here, acceleration due to gravity on Earth is A equals negative 9.8 meters per second. And this is what we're starting with. Begin with the constant of acceleration. So we're just going to write this as A of t is equal to negative 9.8. Okay, we're told the initial velocity is v naught. So what this is saying is that the velocity at time 0 is, instead of a number, we're just being told to call it v naught. The initial position is s naught. Initial position is s naught. So the position at time 0 is s naught. These are basically initial conditions. They're coordinate pairs that belong on those functions. So when I have my velocity function, I have the point 0, v naught. And when I'm at the position function, I have the coordinate pair 0, s naught. Right now, I have neither one because I'm not at either function. I'm on the acceleration function. Okay, so we're going to start here, and we're going to use integration to get back to the position function. In order to use the integration, then we have to add in what we're integrating with respect to. So we want to integrate with respect to time, right? The variable that relates all three of these equations together is time. It's s of t, v of t, a of t. So time is that variable here. So dt, so that we can integrate and integrate dt. So it's always going to be t in these problems. So on the left side, all you're doing is integrating, you're just integrating the name of the function really. So going from a of t back is going to get me to v of t. So this is v of t is equal to negative 9.8t plus c. So we just integrated. This is just my coefficient, so I add on the variable, and then I add on my plus c. And now I use my coordinate pair to solve for the constant. So we're going to take this right here, v of 0 equals v naught, and plug them in. This is a coordinate pair, the t value and then the velocity value. So v naught is equal to negative 9.8 times 0 plus c, and c is v naught. So we'll substitute that back into our equation. V of t is equal to negative 9.8t plus v naught. And I know it's tough because v naught is typically a number, so think of it as a number. It's just a currently unknown number. Okay, it's not a variable, it's a constant. Okay, just like c, Now it's just called v naught. So there's our velocity function, and what we'd like to do is integrate back to the position function. So again, we want to integrate with respect to time. Integrate with respect to time. So on the left side, going from velocity, integrating back is going to get us back to position. Remember up here, we start acceleration, integrate to velocity, again, back to position. So this becomes s of t is equal to, and we're going to integrate here with respect to t, negative 9.8 t squared over 2 plus, remember v naught is a number, we just don't know what it is, it's constant. So imagine if it were 5. If it were 5, we would integrate 5 with respect to time and get 5t. But we don't know what v naught really is, so it's v naught t. And then we, of course, have plus c, because there's always a constant of integration. So now we're going to use the initial condition, s of 0 equals s naught, just like we did over here. We're going to plug in this coordinate pair to solve for c. So s naught is equal to, this is negative 4.9 times 0 squared plus v naught times 0 plus c. And so the 0 terms are gone, and we're left with c is equal to s naught. And we go back and plug that in here to write our final equation. So I have s of t is equal to negative 4.9 t squared plus v naught t plus s naught. And that's the position function. If you look back at your Unit 3 notes, it's one of the original functions that I gave to you to use in that unit. And so we just derived the formula. So you won't do many problems like this. Most of your problems will be really an application of things to find. And so that's what you're going to see in our last example here, number 4. Acceleration due to gravity on the moon is negative 1.6 meters per second. A rock is dropped into a ravine on the moon. How fast is the rock traveling just before it hits the bottom 20 seconds later? So we are starting with our acceleration value. And we can call it g of t, or if you prefer, you can call it a of t again. So we'll start with that. And we're going to want to integrate this with respect to time. So it tells us a few things here in this problem. The rock is dropped. So hopefully you'll remember from Unit 3 that if we drop something, it has an initial velocity of 0. So what does that tell me? What can I do with that? So this means that v of 0 equals 0. 0 is always really nice to work with, right? It makes things go away. It makes my function a lot simpler. So if something's dropped, it's really nice. So we have this velocity of 0 here at time 0. So it's just a coordinate pair that will allow me to solve for that constant when I integrate. Now, the question that I'm given here is, how fast is the rock traveling? So that's not a question of where the rock is or a position. It's a question of its velocity. So I am looking for the velocity of the rock at 20 seconds. Velocity at time 20, which means I only need to get back to my velocity function. I'm not going to need to get all the way back to my position function because I'm not being asked about its position at any time. So we're going to integrate here with respect to time. We get v of t is equal to negative 1.6t plus c. So now we use our initial condition here, v of 0 equals 0. So when t is 0, v equals 0. So v is 0 when t is 0. And this tells me that my constant is 0. So I'll plug that back in and write my new equation, v of t equals negative 1.6 t. That's my velocity function. So now we're ready to hopefully answer that question. Find the velocity at 20 seconds. So v of 20 is negative 1.6 times 20. So that's negative 32. And then to finish, all I need are my units. So if acceleration is meters per second, integrating back once gets rid of the second time condition. And so velocity, meters per second. Okay, and that will end our notes on 5.5.